the last part is, why are we doing stochastic optimization and not purely optimization? So remember yesterday we had the risk function, so the expectation over the data distribution, and I will evaluate this loss function for all possible examples in the universe. This is something that I cannot compute on a computer. Then I have my first approximation, which will give me the empirical risk. So I'm computing the empirical risk on the training set. And the empirical risk, I will sum over all the examples in my training set, and I will divide by this number. But if you have millions or billions of examples, do you really want to compute the loss for each individual examples, for the 1 billion examples, and then use the optimizer to compute one step and move? Or is there something else that we can do to move faster? In fact, I can just sample from my training set, create a mini batch. So let's say instead of using 1 billion of examples to compute the empirical risk, I will just use 10 examples. So capital K here will be much smaller than capital N. And now I have an estimate of the gradient of the empirical risk because I'm using just few examples to compute my gradient. And mini batch would typically be between 10 and 500 or 1,000 examples. It depends on how many examples you can download on the GPU. So it's the idea of mini batch and stochastic gradient descent. We want to move faster. The most extreme case is just to fix k equal 1. For one example, I retrieve one gradient to this example with respect to this example, and I move in the parameter space. But now the sudden approximation here will be very noisy because I'm using only one example here. And if it's a bad example, it can bring me in the parameter space to a place where the model will not be good for the other examples, for the rest of the examples. So it's only to show visually what is happening. So here I'm computing the empirical loss. I'm using all my data, all my examples. Now I create one mini batch here. I can compute an estimate of the gradient, and I give it to the optimizer. And the optimizer doesn't know if it's an estimate of the gradient or not in Adam. It doesn't know it's working in stochastic optimization, but usually this optimizer is robust. There are other optimizers in the scientific literature which really deal with stochastic optimization, but we are not using this kind of optimizer yet. So here we have one estimate of the gradient. We give it to the optimizer. We move in the parameter space. Same thing, after this mini batch, we move in the parameter space, etc. And this one. And so what we can see is that if I don't choose a size of the mini batch for which my data set is, I can divide my data set by this number of examples in my mini batch. If I just have one remaining example at the end here, this example will have a lot of weight, a lot of power, because I will compute I will estimate the gradient with only respect to this example, and it will move all the parameters with this gradient, compared to this example, for which the gradient will be average with the other examples. So the model will be more sensitive to this example because this mini batch has only size 1 compared to size 6 here. So be careful. The size of the mini batch will be a hyperparameter. You need to fix it. So be careful when you fix this value so that you don't have one mini batch with few examples compared to the other. And why stochastic optimization is harder than optimization? In fact, it's like I'm optimizing several functions at the same time. Let's say I'm still optimizing my quadratic function, but now for each mini batch, I have one function associated to it, and randomly I will select one function, and I will compute the gradient, and I will move. So my optimizer doesn't know which function I will choose, because I'm shuffling the examples and creating my mini batch every time. and still I need to converge to a single point. I need to converge to a local minimum. So it's more harder. At the beginning, I will take one mini batch. So I selected implicitly this loss function here. And for this one, I have a gradient which have this name, this one, this name, this name, and this name. So I move a little bit. The next mini batch will select this loss function, and now I will use this gradient. The next mini batch will select this function, and what you can see is that now the first mini batch is the gradient is in the opposite direction. So if I want to minimize the loss of this mini batch, I should increase the parameter h. But if I want to minimize the loss with respect to this mini batch, I should decrease the parameter h. So now you will see the model that will oscillate, the loss function will oscillate for each mini batch because the loss function are not coherent together. I'm just selecting one loss function randomly with a mini batch, and the next time maybe the information will be contradictory, like here. So I move here, and then it will oscillate because there is no local minimum. What I can hope is that I will converge to the expected, to the average. The loss will be the average of all these loss functions, and it will be a given point. But by using this simple algorithm, at the end, my loss will always fluctuate from one mini batch to the other. So we can think that it's harder to do stochastic optimization. Why are we doing it? Because we want to go faster. We don't want to process 1 billion images in order to move in the parameter space. But this noise seems to be problematic. And in fact, it's not that problematic. We discovered recently that the noise can help to avoid saddle point. And using small mini batches can put some noise in the optimization process, and you will avoid saddle point, these problematic points where the gradient will go to 0. With the noise induced by stochastic gradient descent, you can avoid these saddle points more easily. And this is a strong argument to use mini batches that are smaller than very big mini batches. I'm seeing also research to understand more how we can use large mini batches, but they require specific techniques to make it work well. And also, because of the noise that is induced by these mini batches, the model on the validation set will overfit less. The noise induced by the mini batches will help to regularize the network, and the network can generalize well, better than using large mini batch. So the take-home message here is that machine learning is not only about optimization. We don't want to get the global optimum, the global minimum. We must always monitor the validation, the loss on the validation set. And we just want to have good local minimum and fast. Preconditioning will facilitate optimization because we will rescale the parameters so that we try to have all parameters having the same impact on the output, not having one parameter that I need to move by 100 to have the same impact than another parameters that I'm moving only with 0.1. Momentum leads to better results when it's because if the gradients are coherent, I will accelerate. It's like I'm increasing the learning rate by taking into account the gradient information before. If the gradient information are contradictory, then the learning rate is decreasing very fast. So it's some kind of adaptation to the gradient that I have seen before. And noise can be beneficial to escape saddle point, and you should not be afraid to use mini batches that are smaller just because of the noise. It can regularize better. So references that I use for this talk, and thank you very much.